where now each key is each word, and the value is the count of the word I've seen. So it's a very, very simple example, but we can use this as a running example. Okay. So the map just takes your data and converts it into a different key value pair notation. Okay. So the next phase is the shuffle phase. Okay, and what the shuffle phase does is the mapping takes place on all these HDFS blocks, or these blocks on different computers. The shuffle phase says, I want all of the key value pairs with the same key to be on the same computer. Okay, so this is done entirely behind the scenes. This is, when you're using MapReduce, this is not something that you really need to worry about, but you kind of need to understand that this is what's happening. Okay, so it's kind of finding all the key value pairs with the same key and putting them all together. So this is sometimes referred to as the sort step. One thing you can kind of think of doing with this is actually trying to sort the data. You can think of all of the keys with the same. You can think of sorting them alphabetically. So maybe if Am and Apple are close to each other, then they may end up then they may end up on the same machine. This is probably not how it actually works. You would need to program this in. But sometimes conceptually you can kind of encode something that's kind of sorting. And there's a way to sort within MapReduce, and some of the biggest large-scale sorting techniques are actually use some form of MapReduce and use the shuffle step to kind of do the high-level part of the sorting. How it's actually implemented in most simple cases is it's doing something like a random map from the key to each of the different machines. So they kind of want to randomize this. But you want to understand this hash. So you could have two very different things wind up on the same machine, and that's fine, but if the hash is random, it'll kind of distribute them evenly. You want roughly the same number of keys to go to each machine. And we'll talk about some issues with this in a little bit. Okay, then the other phase that you need to worry about is the reduce phase. So MapReduce, right? So what the reduce phase is, it's now got the output of this shuffle phase, and so it has some key. So it's got a key and all of the values associated with the key. So it's taken this, and now it has this data that's kind of been brought. All the things that you want in the same location have been brought together. And so it takes this and it outputs another key value pair. Right? Or maybe it outputs a set of these key value pairs. It doesn't need to be just one. But somehow doing a function on just this data associated with one key. So on this reducer, which is when you refer to a reducer, it's usually one of the machines. It probably has multiple keys that it's dealing with, but its computation should only be paying attention to one of these keys at a time. And now it should have all of the information associated with this key. Anything associated with this key should be on this reducer, and then it can output some function of these. Okay, so if we're doing this this example with word count, and we have when we have two of these documents, which are on. So this is one document. So this is the other document, right? So I've probably mapped them. On the reducer, it's going to get in all of the values associated with one of the keys. So let's say the key was Sam. So it gets in a value like this, and it just adds up all the values. It's very simple, right? So it just adds up these values and outputs the count of all the words. Okay, so this is like, so this word count example has been said like is the hello world example for doing MapReduce. So it's very simple, but actually many of the things you'll run on this, of the sort of things people want to do, end up being very simple like this. So this is called, so just the aggregate function, which is a very common reducer, and this is a very common thing that gets used. You're trying to count some quantity, you look in your value, you see how many times does this occur in each of your in each of the key value pairs on your input, and for each key you have a count, and then you output it, and the reducer adds it up across your whole data set. And you can do this for many things in parallel. So one thing to point out is this is another good example because the input of the data set is big and the output is also fairly big. You need to have one key value pair for every single word. So if you're doing something where you can aggregate all the data on a single computer, then there are a few different systems you can use instead of MapReduce. That's more something that's aggregating the data instead. You can do it with MapReduce, and I think within Google they may have been using it for a while, but then they realized if I just want a single answer, then they built some new systems that that can use for that. And there's part of the whole Hadoop infrastructure that has these other versions as well. So this is a very common example, but there's kind of a strange problem with this example that I should point out. So if you're dealing with a really large set of documents, think of an enormous document so big that you need to store it on 100 different computers. And in fact, they won't all fit in a single computer. Okay, in fact, you can fit roughly, say, maybe 2% of all the data in any one computer. So you have 100 computers, so you have some slack. So what could possibly go wrong with this?
So there can be more data in one of the computers and very less data in one of the computers.
Yeah, that can happen, but why could that happen, right? So at the map phase, initially, it's pretty well distributed, right?
Yes, but on the reduce phase, when you are putting all the data related to one key in one computer. Shuffle.
But shouldn't the shuffle phase handle this by distributing the keys?
Yeah.
So for many cases it will handle it, but remember, I guess I didn't spend too much time on it, but we talked about these heavy-tailed distributions, and one example was the Zipf distribution. And this was a common distribution of the frequency of words, which is what we're after here, right? So it said that something like it's a heavy tail, so it's a pretty wide distribution, but the one word, if I look at just the word the, this word the in many large corpuses occurs 7% of all words. Okay? if it's 7% of all words, and I can only store 2% of the data on any one computer, whichever reducer happens to get the key associated with the is going to have trouble. And it's not going to be able to fit all of the values on that computer. So, so there are kind of two ways to deal with this, okay? So the kind of the easy fix is.
I have a doubt.
Yep.
But it's the sum of the values. So what difference it makes? You need not store all the values of the only the and how many times it has repeated. That's what you store.
Right.
So I didn't understand your point. Like,
Yeah. So okay. So there. So this one I didn't mention. So if I'm looking at these key value pairs, one way I like to process it. I like to process it in a stream. So I just have to scan over the document once. And if you look, a lot of some MapReduce versions have a stream version. So if you use MapReduce on Amazon Web Services, they have a streaming version of it. So it just reads the data once, and if I see the word the, I create a key value pair and I send it off. I start sending it off to whatever reducer it's going to go to. In this sense, then every time I see it, I have to have a one the. I have to have the value 1, and I don't get to add them up until I'm at the reducer. Okay, now, as you point out, this is actually kind of a silly way to do it, right? In any one document, if the is occurring 7% of the time, it should have many the's in that one document. So I should be able to take this whole value, this whole document, and turn it into, say, like the. So I should be able to do something like this, where I say it occurred 17 times, so my key value pair is now the 17, and then down here in this aggregate, I can still just add them up the same way I did before, and it still works, right? So any operation where I can, so any operation where it's cumulative, so you can just do this. You can add before you send it off instead. Okay, and so this extra step, so this is 1. Then there's a step 1.5 in here. This step is called the combiner. So you can optionally run something that's called a combiner, and this will happen on the same machine that's running the mapper before it goes to shuffle phase. So you kind of keep the total counts before you send it off, and this will help. Reduce this problem with the the. So this is what you can do sometimes, but you still sometimes run into problems where you have some key with a lot of values with it, and this one takes a lot longer to handle. Okay, and this process is not done. You don't know until it's finished, until this last reducer is finished. And so this problem is often called the curse of the last reducer. So when you're running a MapReduce job, if it's not very simple and straightforward, sometimes you get stuck with one reducer. It's going to take 100 times or maybe 100 times as long as the average reducer. And so this is going to take the whole algorithm is going to cause the whole algorithm to run a lot longer. So there are a couple causes of this. Sometimes it's because of something like that you couldn't do all the combining ahead of time. So there's this really kind of cool example where you're counting triangles in a graph, and if you're in my class last semester, we spent a lecture on this, and you had to think of an interesting algorithm to get the same answer, but to not have any one reducer have too much work. So you need to algorithmically think about how you organize this to make it efficient. So other times, this last reducer is slow because the machine that's running on, something happened to it and it got slow. right? The MapReduce, the backend, already sent the data to the reducer. So it already sent the data there, but then it was chugging along and it just never finished. So when this happens, actually, the back-end part of the software, the part that you don't have to worry about, will actually occasionally ping these machines that are doing this reducing and see if they're still up. So if these machines have gone down because of something, then because the data is distributed, I can go and do this map and shuffle phase over again and resend the data to another computer that's already finished. So some of this will be taken care of the back end. So there's some things like this we don't need to worry about. All right, let's see. All right, so so in this example, this word count finished in only one round. We started with some data and we did one round of MapReduce and we outputted the full answer that we wanted. It's now stored. What happens is then it's stored back in this distributed file system. All this data is written after a round is written back to disk, still stored in these key value pairs and blocked up into these chunks of these block sizes. So what the good thing about this is the input and the output are both these key value pairs, which means that some algorithms we can't finish in one round. So you can say, I'm going to run multiple rounds and to finish an algorithm. So it's possible to design some algorithms where you need to run it for a small number of rounds. But there's some things you want to do, like if you want to do like Lloyd's algorithm for k-means clustering. This is a very iterative algorithm that we have, right? You assign the centers, you choose centers, you assign points to them. You can think of doing this in the mapping, and this reducing is calculating the new center, and then you would repeat this over again. And you would do this some number of iterations, like 20 iterations. Okay, this is a very bad fit for MapReduce. What happens is it reads this stuff initially from disk because it's going to be stored for a long time, and then when it's done, it writes it back to disk. You think, well, why does it just keep it in? Why does it not just keep this data in memory? Well, when it's done, you want to keep it. You want to replicate it 3 times so it's secure. If you have this many machines, they may crash. So after every round, it's writing it back out to disk again. And so this takes time to write back out to disk. The I/O complexity, the time it takes to write to disk, is often much more than the computation.
So is there a problem set which you cannot solve by MapReduce? I mean, or it is very inefficient to solve by MapReduce?
Well, so like this example of Lloyd's algorithm for k-means clustering is a very bad fit. Like, it's possible to do it, but in some cases, there's actually a cost in between running a new round. It may cost something like if you're using Hadoop, so MapReduce itself is the software internal to Google, which is not publicly available. But Hadoop, the open source version, is written in Java, and it's actually fairly slow because in addition to reading it from disk, it's also booting up the virtual machine and getting things started, and it can take 5 or 10 minutes in between rounds. So doing 20 rounds is going to cost you at least 20 minutes. And really, you would think you should be able to avoid this somehow. Okay, so this has led to a couple of interesting things. One is, there's some people who looked at the algorithmic analysis of this and they said, these rounds are really expensive, so let's try and design algorithms that use the fewest number of rounds. And really, if you're using Hadoop, you probably should be trying to use a small number of rounds to try and compute within this model. But then it's led to some other systems. So this was, MapReduce was a paper published, I think, in 2003. And when it first got published, there was a lot of controversy. There's some people in databases who wrote some article saying that MapReduce was a giant step backwards. It's really slow compared to a database system and so forth. But it also led to some new system design where people have figured out how to make this more efficient, especially in between rounds. There's one system that's called RAM Cloud, where essentially they're able not to really use the disk. Everything is kept within memory. Things still backed up on disk, but they're able to kind of ensure that it stays back up even if things crash. They can still recover within the memory of the computer. There's also the more kind of thing that's gained more popularity is another open source system developed at Berkeley called Spark. So Spark is essentially, you can run MapReduce, and it's kind of an alternative to Hadoop, but it tries to keep as much stuff in memory as possible. And it does some stuff where it keeps, if a machine crashes, you don't have to reread it from disk, you can kind of reconstruct it from other stuff in memory. And they have to keep some extra overhead to do this. And this was many years of development. It was much more complicated to figure out how to do this without writing it to disk, so it was still as resilient as MapReduce and Hadoop was. But now this is starting to be used. It's starting to be a viable alternative. So if you hear of Spark instead of Hadoop, that's something that'll allow you to do a lot more rounds more quickly. And so that's so probably 2 years ago, Spark was just kind of announced at that point, but the round issue was still really something people talked about. Now people realize if you're using Spark, you can do things that will take a lot of rounds. You can do k-means clustering that way, although you still may not want to do that. You can do a lot of machine learning algorithms like logistic regression that are very iterative in nature, and those work well within Spark. Okay. Okay, so now I was just going to go through a few more example programs. So we'll spend on Monday going through some slightly more complicated things about how to do PageRank inside MapReduce. It was one of the two big initial kind of very compute-intensive things that Google was doing every day that they designed MapReduce for. They designed it for PageRank and the other thing, which is building this inverted index, which have both fit very naturally into this. But then they realized that this was useful for many other things, such as analyzing logs and so forth, and those look a lot like word count. You scan something, try and find how many instances of something there is, and then kind of do some aggregation or summing of these things on top of it. So let me have one chance just to spin this around. All right, so let's do another example. Okay, so we're going to see how to build this, inverted index. So if you remember, this was what the search engine, the access to this search engine looked like, and we're not going to talk about how do you rank it. We're going to talk about how to just you have a bunch of web pages. They're full of words. You want to know for each word every web page that this word is on, right? So the input So the input is a bunch of web pages, and they're full of words, and the output is you want to have the key being the word, and then the value being the set of all web pages that have that word on it. Okay, so what are we going to do for the map step?
So we collect all the words and assign those as keys, and for each word we assign the web page which was the key as well.
Oh yeah, that's right. Right. So it's very simple. We're going to create a set. Create a set of these key value pairs. Each key is going to be the word that we see, right? So example could be the word pie that I was using on Monday, and then the value is the page that's on, right? So if you're processing one initial key value pair, which is one web page, everyone will have the same page, and you can have all the different words which are on that page are going to have a distinct key value pair. Okay, so this is the map step. That's all we had to do. We just converted it into this. Okay, so then we don't have to worry about the shuffle. That takes care of it for us. So we then need to reduce, and the input is going to be one word and a bunch of all the pages. Okay, so this is the input to the reduce step. So what do we have to do?
Nothing.
Right, it's already done. We don't have to do anything in the reduce. It's already there. Right, so this was a very natural, they thought this was a very natural thing to do, to build a big system that actually did this. Right, so they built a big system that built this inverted index, and they said, let's structure this as the map and reduce. And so map and reduce come from, if you studied programming languages, they study these paradigms of computing. And a MapReduce paradigm is a very common paradigm. They just built a big system that took care of this to do it in parallel very efficiently. So building this inverted index was a very natural thing to do within this thing. Okay. So let's look at one more slightly more complicated problem. So we're going to have the same input as before, and so now so the same input as before. We're going to have web pages. Have web pages. They have a bunch of words on them, and what we want to do is something. It's maybe kind of silly, but we want to look at all of the. We want to look at all the 3 grams. So that's sets of 3 characters that appear consecutively. And we want to find if there are any 3 grams that appeared on a single web page, and tell me where those web pages are. Okay, so how would we do this? Okay, so we just need to do these 2 steps. So what is the map phase here? Right, so so we're going to take this web page and we're going to process this in a stream. So we're going to stream over these words, and for every 3 consecutive characters, we're going to write one of these. We're going to write one of these 3 grams. We're going to write it out with the value being the page. Okay. All right, so now we don't have to worry about shuffle. We get to the reduce. We have sitting there each 3 gram, and we have a set of pages it comes from. So again, we want to find if there are any 3 grams that appear only on a single page. So what do we do?
Count. Do we run the word count thing on the values so that we get the count for each page and the number of time couples?
Yeah, we can do that, but then we're going to get each 3 gram and a count, right? We want to only know the 3 grams that appear in a single page. So that tells us how many times they appear. So that's probably pretty useful. So we can do something. Where I can write 3 grams and I can do a sum over the number of pages, and I sum up 1 and I'm going to get the number of pages that's on. So, but this is not quite the answer we want. I could have a 3 gram that's on 2 pages.
So, do we go through each, do we count the number of times each page occurs for the particular 3 grams? So, if we have, so we are trying to find how many times a 3 gram occurred in one particular page.
So I just want all the 3 grams which are on a single page, and I just want to store the set of those.
I don't know if I'm totally following you, but I feel like you could go through and then start counting how many pages each 3 gram has, and then if you hit 2, then just move on. And if you don't hit 2 pages,
Yeah. So
that's your count.
So basically, I wrote this out here, so it's on page 1 through page K. Those are the pages I have, right? Right, so basically what I want to do is I want to look at this set of pages. If there's only one thing in the set, I want to write it out. If there's more than one thing, then I can ignore it. If it occurs 0 times, I've already ignored it. Right, so it was pretty simple though. Right, once probably more understanding the problem than trying to figure it out. And this is very common. It's very simple to write these, and you know, I've heard if you're doing analysis inside of Google, you're very often using these tools. They're very easy to write a simple thing to analyze some structure that they have. And so you just have to write very simple code to kind of write these both steps, and you run it, and and it will automatically take care of the parallelism, the storage of this, the robustness when nodes go down. It'll take care of all that in the background.
I'm just wondering if there is a program that converts our algorithm into MapReduce, or if someone can
So
build
let's
that.
say you're doing something like dynamic programming, like you're trying to match 2 strings. So you want to convert that into MapReduce.
Yes, so I mean a general program that converts the program that we usually write for one computer to a MapReduce program. I mean, we can build.
So that's okay. So that's pretty much the wrong way to think about it.
Okay.
So really, the thing with this is, it's a new way of thinking about how you would write your program. So this is the part probably where you need to think. Right? There are multiple ways to write a program. You can write one. You can sort lists using the bubble sort, and I can convert that to MapReduce. There's 2 reasons why that would be stupid. One, you know, unless my data is basically already sorted, you shouldn't use the bubble sort. 2, if you use the shuffle phase intelligently, you're going to do the sorting much better, and then you're hardly writing any of the MapReduce code. So you shouldn't think of converting a program the way it's written into MapReduce. You should think of writing an intelligent program within these confines, within this mapping and reducing paradigm. And it's kind of, you need to go through examples and think of different ways how to do this. It's not, it's a slightly different way of thinking about it. So these were really simple examples, but hopefully you're kind of getting the idea. We'll talk about doing PageRank, which there are a couple different variants of it, and hopefully you'll see some of the, like a little bit more of the nuances of how you do this. But again, even in all of those things we'll be talking about, the program, the map step, and the reduce step that we choose to do will correspond to a very small amount of code. So now if you are thinking about converting this, you don't want to think about a regular inline program. There's been parallel algorithms studied in computer science for for a few decades. There are multiple models of parallel algorithms. The most famous one is called PRAM. And people have tried to understand how PRAM relates to MapReduce. Turns out that's really the wrong thing to do. There's another model that's called BSP, which is kind of you do a bunch of parallelism on each machine individually with its own memory, and then you stop, and then you trade stuff, and then you do it in each, and it works in rounds. And that's much closer to what happens in MapReduce. And so there is a way, if you have an algorithm that's written under the BSP model of parallel algorithms, to convert that into MapReduce. There's these reductions that you can do.